Okay, so we can begin the lecture. Slav Petrov is a researcher at Google Research in New York. Born in Bulgaria, raised in Germany, he did his master's in computer science at the Free University of Berlin. He did his PhD in the same area at the University of Berkeley. He now works at Google Research. Nowadays, he leads a team that works in natural language processing and investigates machine learning. He also teaches statistical natural language processing. So let's welcome Mr. Petrov.
Hello? Right. Do you hear me? Yeah. Okay. I can hear only myself, but is the speaker on? Yeah. Okay, cool. Thanks for the introduction. Thanks all for coming. It's a big lecture hall, but feel free to ask questions. I don't want to just talk for an hour and a half. And I tried to kind of put together a somewhat high-level talk about things that I work on and other people in general at Google. Listed a bunch of names of people from my team and people that that have contributed to the things that I'll show. Before going into the technical part, Gonzalo and Magdalena had asked me to say a little bit about how I got into computer science and who I am. So I made this slide this morning. As you just heard, I was born in Sofia, moved to Berlin, grew up there, went to grad school, or did my PhD in Berkeley in California, and now I live in New York, and currently we're in Portugal. Shortly after I moved from Bulgaria to Germany was the World Cup '94, where Bulgaria beat Germany. And I'm a big soccer fan, which is somewhat related to why I'm here, in a way. So when I was in Germany, before finishing high school, I attended some seminars at the university, and we spent a week proving the four-color theorem that you can paint any map with four colors so that no two neighboring countries can have the same color, which I think is a very exciting result. And actually writing an algorithm to do that is it's non-trivial, but it's quite feasible. But proving that it's always possible took forever to do. And at that point, I realized that I don't really like just math and proving things for the sake of proving them, but actually like more practical things and building things. And so that's why instead of doing math, I decided to focus more on computer science. And as I was doing my undergrad studies, I saw a room in the basement where there were some soccer-playing robots. And the team that we had was called the Foo Fighters from Free University. Foo Fighters was quite good, and I got involved with them and worked on detecting the ball and the position of the robots, and also specifically on making the goalie better. In 2004, when the Euro Cup was here in Portugal, we actually had the RoboCup World Championship also in Portugal, in Lisbon. So that was the first time I came to Lisbon, and it was great because we won. You guys were close, but that was sort of my first exposure to computer vision and machine learning. And based on that work, I continued working and did my master's thesis in this area, and then decided to go to grad school. At first, I worked on hand recognition and computer vision, tracking fingers and hand movements. But then I tried to take some of these machine learning ideas and apply them to language, and I ended up doing my thesis on natural language processing, where instead of playing with fun soccer robots or looking at cool images, I was producing these somewhat boring parse trees for sentences. And I always used to say that I'll go back to computer vision one day, but now it's been almost 10 years that I work on language, and I'm actually quite excited about the things that we can do with language. So in the background, we do still produce structures like this, but the applications are quite exciting that we can do nowadays with language. So this is a brief summary of kind of how I got into this field and why I do what I do. When giving talks, I like to sort of contrast what we can do in reality and what Hollywood has been able to do for years and decades. And so, how many of you are born in the 80s? Okay. 90s? Okay, good. Yeah, so this is before your time. This is when I was born. So we had R2D2, probably you still have heard of these robots. They could talk and walk and do useful things and even had feelings to some extent. The reality was black and white, a little more grim. Rule-based approaches used to be the predominant approaches to artificial intelligence. We would ask experts to describe the world and say, okay, given this precondition, this is going to happen. So you can think of it as a giant collection of if statements. And there's always an exception to the exception to the exception, and this is not very scalable. So there were some early successes, but it didn't AI didn't quite deliver what it was promising. So a nice metaphor that I heard once was from my advisor in computer vision, who said, like, just because you can climb a hill doesn't mean that by doing more of that you'll get to the moon. And I think that was somewhat of just kind of, there were some inherent limitations to these approaches. On the other hand, using kind of expert knowledge and linguistic knowledge in natural language processing, I think is more current nowadays than it was 10 years ago. So I'll show some examples for that. It wasn't all bad. In the 90s, we had self-driving cars that could also talk in addition. I guess this is partly biased by my German upbringing. David Hasselhoff and Kit. In reality, people were starting to use statistics to kind of make progress. The problem was that the computers were pretty slow. What you have nowadays in your pocket as a smartphone is a lot more powerful than what desktop computers or even big mainframe computers could do in the early 90s. And so it was just difficult to tackle real-world problems with these small computers. And the other problem was that there was just not enough data. When thinking about natural language, a lot of the progress has come from the availability of large amounts of text in digital form, and the internet wasn't there, so we didn't have that. Now, kind of in the early 2000s, like robots in movies were cute and nice and had emotions and everything that humans do. But the reality was still not quite there, though we started to kind of catch up to some of the early stuff, potentially. Google Translate, I'm listing here 2007 because that's the year that it switched from using third-party services to just being a completely in-house system that was based on statistics. And I'll show some kind of high-level examples of how it works. Speech recognition has been around for a long time, but I think 5-6 years ago, like, it really got much better. And then in the last 2-3 years, we have seen another wave of improvements coming from deep learning and neural net methods. And then a few years ago, Google announced the self-driving cars project. Nowadays, cars can drive under many conditions and oftentimes better than humans, because in addition to the two eyes that we have as sensors, they have a wide range of additional sensors and information. And if all cars were driven by computers, we could put a lot more cars on the streets because they can communicate and cooperate in ways that humans trying to take advantage of kind of the road conditions and trying to get past others don't want to necessarily do. And so it would be a win-win potentially. eventually, but legislation needs to catch up, and we need to kind of figure out how to do this properly. What would happen if there was an accident? And I think this in general is a big question for artificial intelligence, is the question of sort of ethics, like what are we allowed to do, and who's responsible if something goes wrong, that we'll need to figure out. But I think it's going to come in some form or another, and it will be great. It will allow us to focus on other things and to drive when we want to drive, but when we're just trying to get from A to B, we can focus on other things rather than wasting half an hour every day in our daily commute. And then one thing that is closer to what I'll talk about is Apple Siri system or the Google Mouse system, where we're trying to get towards natural language communication with computing devices. So rather than typing keywords in or pressing buttons, there's a movement towards just asking the computer questions and getting back answers, or having a dialogue. And I think this will really change the way that we interact with computers. And as the devices get smaller, it's just clear that the typical kind of keyboard way of interacting with a computer or mouse is not going to work. And so we need to integrate speech recognition as well as language understanding, and form that way a system that we can talk to the way that we would talk to a person. And I'll show some examples there. Any comments, questions? All right, there's not much to ask yet because I'm just giving general overview. But let's look at an example of something that works reasonably well. How many of you have used Google Translate? Maybe I should ask the opposite. Has somebody not used Google Translate? Okay, good. One piece of advice that I tend to give audiences that are not native English speakers: if you're trying to go from language A to language B, where neither of those languages is English, in many cases, the translation will go through English. So I'm not sure exactly about Spanish and Portuguese, actually, when you translate directly, whether it's going directly. But if you're going from Hungarian to Portuguese, it's going to go through English. And so oftentimes, I assume you understand me, so I assume you understand some English. Your English, in many cases, will be better than Google Translate's. And so try to make English one of the endpoints, and your translations will get typically better. And that's because if we have n languages and we want to translate between all pairs, we would have n squared systems that we will have to build. But, and we support, Google Translate I think supports now more than 80 languages. So 80 squared systems would be quite a nightmare to maintain. But if we go through English, then we just need 2n systems, and that's a lot more manageable. But we do also look into how to bridge more effectively between the languages, and in cases where the languages are related, try to translate directly, because you then just get better quality. But in many cases, for example, for, I don't know, Finnish to Japanese, there will just not be enough data to train the system anyway, so you need to bridge through something else. So here's an example that I pulled out last fall, I think. We haven't updated the system, so the quality should be similar. The next push is coming up now. How many of you speak French? A few. And the rest with Portuguese, you can kind of understand maybe a little bit what's going on. But if you don't, you can just go to Google Translate. Or if you're using Chrome, it will ask you whether you want to translate it. And you'll get the following text. Nobel Prize for Medicine was awarded Monday, October 6th, for a half to the Anglo-American John O'Keefe, and the other a couple of Norwegians, May Britt Moser and Edward Moser first.
They are rewarded for the work that helped discover a brain system of internal GPS permitting an orientation in space as complex as this environment. There are a couple glitches here and there, certainly not to the quality of a native speaker, but it's quite readable, and if you compare with the original text, you'll find kind of maybe some things are not perfectly translated, but overall it's quite good. But I'll show some examples for other language pairs where it's not as good. And so, but before doing that, I thought I would kind of do a 5-minute explanation of what's happening behind the scenes. Do people know something about statistical machine translation systems and how they work? Like, does anybody know? 1, 2, okay. So that'll be something new. Good. Hopefully you'll remember that and you'll learn something. So to make this more exciting, and so that you cannot cheat by knowing the languages, here is a made-up sentence that comes from Kevin Knight, where the task is to translate from this artificial language Centauri into Arcturian. And this is the string that you're trying to translate. I'm making things easy for you by giving you white space, and so that they're separate words. In Romance languages or European languages, this is typically the case, but many Asian languages, for example, don't have that, so you would need to first figure out what the words are, but we're simplifying here. And now if I ask you to translate it, it's not much you can do right now because you don't even know what Arcturian is and how the hell are you supposed to predict the words. So I'm going to make this a little easier and give you what we typically call parallel text. Sentence pairs that mean the same thing. And in this particular case, they're actually quite literal translations so that it's easier to find them. The real systems that we have are not always sentence-aligned translations, and so it's a little bit messier. But here are 12 sentences, and now if I asked you, can you translate the sentence at the top, given this database of sentences in their translations, how would you approach it?
Matching words on
Yeah.
those lines.
Yeah, so you take the first word and you try to match it and see sort of where does it occur and can I figure out something about it. So if we take the first word, Farak, it occurs twice. So it occurs here and here. Now we can look at the other side and check like, oh, is there a word on the Arcturian side that appears in those two sentences and therefore is likely to be a translation of that word? Well, yes, turns out this word jad appears in both sentences and all the other words are different. So we cannot be completely sure, but it's a fairly good candidate to start with. And then we can continue. So we can look at, Sirach. It occurs once. For things that occur once, any of the other words could be the translation, so we don't really know much. So we need to go to the next one and kind of keep going, trying to disambiguate things when there's a clear candidate, and in cases where it's only one occurrence or there are multiple words that occur in both sentences, we don't have enough information, so we proceed to the next one, and then by elimination we can then continue even looking up words that don't occur in the sentence that we're trying to translate, but then kind of using elimination, then we can say, oh, these two words align, so then that limits the chance, the options for the other words. And if we keep doing this, then we'll get a dictionary giving us pairwise translations between the words. And then we can go back to our sentence and line things up. Turns out Sirach actually is a word that gets dropped. Happens sometimes. You don't have to translate everything literal. It might become an ending in the other language, or it might just not exist at all. In some cases, in real-world translations, you might have one word translating into multiple words as well, or new words being inserted, and that we couldn't really handle with this approach, because so far we have only constructed a dictionary, a phrase table for individual words and how they translate. Nonetheless, this gives us now this kind of sequence of words. And is this a good translation, do you think? Or is there something else missing that we didn't model? Particular, what about the word order? Right now it's all monotonic, so every word keeps its position. If the languages are related, like French and English, that's a good approximation. You might want to switch some order of adjectives and nouns here and there, but it's mostly local and it will be still understandable. But if you have language pairs where the two languages have very different grammar, that will not work so well. And let me show you what happens when you apply such a method to Japanese. Do we have any Japanese speakers? Okay. Well, I don't speak any Japanese either, so I had to dig around to find that article. Yes, I was wondering where that's coming from. And so if we take this Japanese article and run it through Google Translate, we get the following. It was supposed to be serious. Blue light emitting diode was decided to Nobel Prize in Physics in the invention of LED. Isamu Ozaki, the 8th professor, Meiju 85 of the disciples in the co-winner Hiroshi Amano, Telephone Roundtable Asahi Shimbun 54, Nagoya University professor participated in. It was a renewed joy in the master and pupil. So you start reading a little bit and it sounds great, and then it just jumps to another topic, and then you get a little bit and you have hope, and again it breaks down. And so what's happening is that the Japanese word order is so different from the English one that even though we do a lot more than what I just showed, we still, Google Translate is not able to figure out the correct word ordering. And so things are coherent in little chunks, but the overall sentence structure is completely garbled up, and therefore the meaning is not preserved at all. And we get the topic. We know that it's still talking about Nobel Prize in Physics, but it's not really understandable what exactly is being said. And so to get the good translation, we need to model not just the meaning of each individual word or phrase, but we need to put them together in the right sequence. And the system is trying to do that. It's just failing when the difference between the languages is too big. So nonetheless, here is an example for some language pairs and what happens when you add more data. So in the little example that we did for Arcturus, we saw that it can help you to have more sentences so that you can disambiguate words even if they don't appear in the words that you're trying to translate, because they eliminate options for other things. And so similar things happen in real life, where here we have the translation quality, and here we have the number of sentences that we use for training the system. And so 1 million, when we go to 10 million, everything goes up. If we go to 100 million, things get better again. If we go to 1 billion, things get even better. And in some languages, the curve is climbing a little higher. Somebody asked me, why is Portuguese benefiting so much? I don't actually know in this case. But overall, more data always helps. And in some cases, also helps more than smarter models. But in order to get the real understanding, just data is not going to be enough. We need to also do something on the modeling side and improve the models. So it's always a combination of finding efficient ways, efficient models that can leverage these large amounts of data, and then harvesting as much data as we can so that we can get to better translations. But for Japanese, we will need to do more, and I'll show you one example of what we do there by using grammar explicitly to try to improve it. A different application is question answering. And with mobile phones, and especially with Siri, there's been, after Siri, I should say, now Google Now as well, there's been a lot of progress in this area. This is an old screenshot that I have from when I was a grad student, where when you ask what's the capital of Wyoming, Google tried to provide an answer, which back then was called a web definition, and said Cheyenne is the capital and largest city of Wyoming, based on this link. Nowadays, there's a much more confident answer provided on the top and additional information on the side that is extracted from a structured knowledge base and highlights the most important things. You can think of this as kind of a distilled version of the Wikipedia page. In many cases, it is based on the Wikipedia page, but then it also incorporates additional information. And the trend is to do more and more of this. For simple questions, like what's the capital of Wyoming, or what's the population of France, it works quite well. Actually, you don't even need to say what's the population of France, you just say population France, and it will give you a result. But I say no understanding because in many cases, there's fairly simple systems behind these features that try to answer specific types of questions. And just slight variations of the question break things. So this is a slide that I made a couple years ago and that I've been using to then show, look, we have this nice plot here, but then if we say, what was the population of France in 2002, even though the data is there, we just need to pick out this row. Like Google used to not be able to do it, and what's even worse, it even didn't show you this table, this plot anymore where you could have gotten the information yourself. Now it's all gone, and you get these results that are much less useful. But I said used to because since around Christmas, we can actually now answer these questions. So this is a screenshot I made this morning. What was the population of France in 2002? Now you get this beautiful, even nicer plot with a highlighted dot here on 2002. It shows you what the population was, and you even get a bunch of other related statistics. So things are getting better, but to get to sort of real understanding, we'll need to do more than think about what are the questions that people ask and explicitly encode them with specific techniques. We will need to do something more general and principled where the system is learning continuously. So for example, when you search nowadays, you get 10 blue links. And if you click on the third link, we know that the first and second links were not that great, and so the system can be adapted, and it gets better over time. Well, for these question answer things, the click usually isn't there anymore. You just look at the information and you're done. Or you might mark it and copy paste it somewhere. But there's no explicit feedback that's given as to whether something was good or bad. One can try to derive it from the subsequent query, whether if it was a refinement of the previous one, then maybe we didn't quite get it right. But if the session stops there are two reasons why it might stop. One is we nailed it, we gave you the answer, you're done. The other one is you were just so frustrated that you gave up and you don't want to try anymore. And so figuring out how to leverage that feedback is non-trivial, but we need to do that in order to learn language sort of in the wild, because asking humans or linguists to annotate everything for us is not going to work. But we will need to ask humans to annotate some data, then we can learn from it, and that can generate new data that can then kind of be exposed to humans, and so get into this nice virtuous cycle to get better. That's at least one hypothesis of how we might get to build systems that really understand language. So To support some of these things that I showed, what we're doing in parallel is to change the way that we think about the information, how it's organized. So when you think about the internet, you think about websites, and they mention, they have some information about particular entities. So entities are basically anything that has a name. So people, places, companies. These things have attributes and relations between each other. And so one particular web page might talk about all the types of painkillers that are out there. And another web page might talk about the particular side effects of a particular painkiller. And so if we think about it in the documents and setting, then you have lots of documents that contain the information that you might need in order to answer a query. And so flipping it over to collecting and grouping the information by entities allows you to take the information from multiple places and just say, okay, if you care about Barack Obama, here's all the information that we have for him. And then you can try to answer questions based on this entity attribute relation database. And Google has been talking a lot about the knowledge graph. It's a natural way to represent things in an entity-centric world, but that's just one possibility. There's other ways that one could do it. There might be probabilities attached to these things to say, well, how confident am I? If it's coming from Wikipedia, maybe I'm very confident. If it's coming from somebody's blog, I should be less confident. And then this information can be used to answer questions. So I already showed some examples of the kind of population and capital of states form. Here's another example. Who is the president of the US? This question will be answered now in more than 20 languages on your mobile phones, as well as on the desktop. But what you can do these days in English is that you can ask a follow-up question. And namely, you can say, where was he born? And if you talk to your friend, that's how you would talk. But when you're typing in your computer, you'd probably never type he in a query because it's ambiguous. You don't know who is he, and how is Google supposed to know who he is? Well, on Android now, or actually I think if you're using the Google Now app on any mobile phone or tablet, we will keep the information from the session because we want to have a conversation with you. And so when a pronoun like he is mentioned, we'll analyze it and we'll say, oh, there's a pronoun. This must be referring to something in the world. And if it's not in this query, then likely it's in the history. So let's try to figure out what it is referring to. And what we do in the background is that we take every query and we analyze its grammatical structure. So we do part of speech tagging. We say, okay, this is a noun, this is a verb, this is an adjective. And then we also say, what is this structure? Kind of, what is the main verb? What is the subject of that verb? What's the object? And so on, to give us a structured representation of the text. And then based on this analysis, we then do also entity detection and extraction. So we'll say, okay, there's an entity, which is the president, and we know that it's a type person. Then this is not us, but US, just lowercase. We have figured out that this is a location. And so then in the next query, where was he born, we'll see, oh, he is a pronoun. But pronouns refer to entities. And since there's no entity explicitly mentioned here, we look at the context and we say, oh, look, he must be referring to the president because that's a person. And we don't have any other people that it could be referring to. And so then we can substitute Barack Obama for he and retrieve the answer Honolulu. To show you that this is not just a random fluke, we can ask who is his wife. Again, there's a pronoun, in this case his. and it's a possessive pronoun, but most importantly, it's masculine, and so it refers to still to the president. While wife is another entity, and we know that it's going to be female. So when we ask where was she born, we know, oh, she is a pronoun, it's ambiguous, but it's feminine, so it can only refer to wife, but wife was the answer of this query, which is Michelle Obama, so we substitute Michelle Obama for she, and we get the right answer, Chicago. And this works for English, has been working for half a year or a little more, maybe a year. Some people are using it. Many people don't know about it. That's why I advertise it. But it's also not working always, so there's no big advertising campaign for it. But we're trying to get in this direction where you can use he and she and it. Similarly, when you're asking for directions, it's very natural to use here and there. Every human being will understand it. Google.com until now didn't, but we're moving in that direction that you can use these relative pronouns as well. And additionally, we want to do this not just for English, but we would like to do this for many languages. And so try it periodically throughout the year. Hopefully by Christmas, it will work for Portuguese. It's something that we are working on, in particular my team is trying to help put together, because the multilingual aspect, I think, is very important. A lot of academic research is focused on English, and English is spoken by a lot of people, but we shouldn't neglect the other languages. And so in parallel to analyzing queries that are entered or spoken into Google, we also analyze documents. So here, this is just some snippet from a newspaper article. No need to read it. But we do the same type of analysis, part of speech tagging and parsing as before, just not showing them because they take up so much space. And then we do entity detection, and then we resolve these pronouns called coreference resolution. And furthermore, we then take the entities and we ground them in this knowledge base that I showed, the knowledge graph. So we know that Barack Obama has a profile there, and so we have resolved Barack Obama, Obama, Mr. President, he, his, that they all refer to this male entity that's a person and has an entry. Freebase is a publicly available database in which we have also resolved it. And we even have a link to the Wikipedia article, so that we have the information in one place, because that allows us then to do relation extraction, figure out what is the relation between Barack Obama and the Democratic Party, for example, and then we can check our database and see, oh, do we have that relation already in there? If we don't, then we should enter it. And that's what we do nowadays, is that as we index documents on the web, we try to analyze their structure and then figure out either relations in there that we want to supplement our database with, so that we can answer questions that are not answerable before that from the database. Okay, any questions? Yeah, please. Yeah, so it's a good question. There's another aspect of it, which is also that on google.com you get advertising, and if you provide the answer, people might or might not interact with that advertisement. Overall, I personally never think about this on my day job. I'm trying to answer questions, and the people working on search quality, they're focused on providing our users with the best possible experience. And when you're searching for information, then the answer is what you're searching for. When you're searching to buy something, then an ad is actually oftentimes a useful bit of information. But yeah, in this case, when you're asking where was Barack Obama born, you're not really looking for flight tickets to Honolulu for your vacation. Like if you were, you would ask a different question. And so, yes, there are financial implications. By providing the answer, Google might get less money. The content providers might also get less money because people don't go to their page. But in both cases, I think the effects are fairly small because nowadays advertising online is not just, you don't pay for the view, you pay for the interaction, for the click. And so the fact that there's an ad on google.com or on somebody's blog, there's no money changing hands until somebody clicks. And so even if you go to somebody's blog and you read the information there, unless you click on the ad, he's not going to make any money. And so in many cases, the effects will be small. But it's important to kind of, yeah, keep the content providers in mind, especially when it also comes to newspapers and other sources. And that's why there's always attribution of where the fact came from. And you can kind of verify it yourself by going to that site and continue to drive traffic. We don't, like, unless we own sort of the ground truth and we're 100% confident, we'll always show the link. And so traffic will hopefully kind of not diminish too much. But yeah, it's something to keep in mind. Other questions? Yeah. Okay, so Freebase is a free kind of open source database, knowledge database. It was created by a company called MetaWeb, and Google acquired that company, but decided to keep the resource open source and to keep it available for both academic research as well as other companies. And so I'm mentioning it here because a lot of people who kind of work in this area are familiar with it. Yeah.
You were mentioning the knowledge graph where you put new data, and is it automatically inserted, or is someone curating the new data?
Yeah, so the question was about knowledge graph and how the data gets in there and whether there's human curation. And so it varies. Basically, there are systems that try to just ingest other kind of pay for or free resources like release dates of CDs and other databases that you can just map one-to-one fairly accurately, and somebody has humanly curated those and you can trust them. But then when you go to web pages and you try to extract facts on your own, you typically don't want to trust a fact if it's extracted it once on one page. What you kind of require is some type of confidence, and a good way to get confidence is to find it on another page again. And so we have automatic systems that try to supplement new facts to the knowledge graph, but there we try to have like 99-point-something% accuracy. And to get to that level of confidence, you need to find that fact in multiple places. Overall, we are also trying to have kind of a knowledge graph with ground truth things, as well as a kind of more probabilistic version where we might have a lot more information. And there we might have probabilities attached to it. And so then it becomes a question of, okay, do I use now this information to supply the user an answer or not? What's my confidence? The problem is that confidence estimation is very hard. If you knew how to estimate the confidence more accurately, then you could use it as a feature in your prediction and make your prediction better. And so you have a little bit of a chicken and egg problem. But we try to kind of put some confidence on the automatically extracted things. And whenever we show something to users, it needs to be in the high 90s. And we don't want to show anything that's wrong. So oftentimes we have the luxury of being able to trade off precision and recall. So when you enter a query, the expectation is that you'll get 10 links. If you get an answer, right now it's mostly considered sort of a bonus. And so we can be very careful to only show the answer when we're very confident. We could show many more answers, but then our accuracy would go down. And so that would increase the recall but drop the precision. And we try to stay in a very high precision but low recall range. Was there another question? Okay. Cool. So let's look at a couple kind of examples of what's actually going on. Before I do that, how many people have kind of machine learning experience or taken a class or done something? Okay, some. So kind of in traditional natural language processing, but also kind of supervised machine learning, what that actually means is, if you want to be very kind of blunt or pessimistic, it's just counting and dividing. You're estimating probabilities based on some data that somebody labeled for you. So if you have the word book and you want to know, is it a noun or a verb? Well, you didn't just go through and you count in a corpus that linguists have labeled for you. They've marked up. This time it's used as a verb. This time it's used as a noun. You go through, count, divide, you get some probability. And then to generalize it and to make it better, the fact that it's 70% of the time a noun and 30% of the time a verb is not helping you much, because you want to get to something that's closer to 100%. And then you start looking at the context and you say, well, if it's preceded by the word the, then it's going to be probably close to 100%. And so you don't want to write these rules explicitly by hand. You want to just say, kind of use generic features, like look at the word before and estimate the probability conditioned on that. And so that's basically what these models do. And kind of to improve them, we can just ask linguists to label more data for us. And so for syntactic parsing, what we do is we just ask linguists, okay, can you take these sentences and just mark them up with noun, verb, adjective, and then which word modifies each other one. And then my work is then to take that and to build more accurate models. I'll show just kind of at a high level, give you some intuition of some of the things that we do. And I won't go into the details of these two different approaches, but roughly speaking, there's kind of two ways to approach the problem. If you have a sentence and you're trying to decide which word modifies another word. In the graph-based one, it's maybe easier to explain, is you just try all combinations. You take all pairs of words and you try to compute a score. How likely is this word to modify the other one? It's great because it really checks all possibilities, but it's fairly slow because you need to check all possibilities and then find the best combination of them so that you get a full analyzed tree, connected tree. In the transition-based world, you read the sentence from left to right and you try to disambiguate things as you go, because the intuition is, well, we humans do that. We don't have to read the whole sentence and go back multiple times and kind of iterate over it. We just listen to it, and then sometimes we delay some decisions. So there's a stack where you can delay decisions, but you can do it roughly in linear order. If you then compare time, meaning the time for the analysis, parsing time, how much computation do you need versus what accuracy you get, these transition-based approaches, especially the linear ones, are very fast, but unfortunately not very accurate. And so you can add a beam where you keep multiple hypotheses that compete with each other, and you can increase the accuracy that way. Or you can do this exhaustive search for the best combination, and there you have different types of models, and how many words do you consider at a time? Do you consider only pairs, or do you take triplets of words, and so on? And when you take more words into consideration, you get better accuracy, but things get very slow. And so since we want to analyze the web and also all your queries in a fast way, you don't want to wait for a minute before you get your answer. We need to do this in a fast way. And a lot of our work is to do this at the highest accuracy possible, but in a reasonable amount of time. And so one line of work that we have done is to try to take these models and make them faster. And another one is to make these fast but not so accurate models more accurate by using more data and training them to to do better. Who is interested in syntactic parsing and grammars more? 1, 2. Okay. I think I'm going to skip it, and I'm happy to talk about it more afterwards. And I'll show more examples instead. Maybe I'll show one plot because it's interesting. Because we always think that language is very complex, but in reality, it's not that complex. So what I'm showing here is the distance between two words that modify each other. Well, I guess they don't modify each other, where one word modifies the other, based on the part of speech tag of that modifier. So adjectives will modify nouns, like the red chair. The also modifies chair, so the determiner the is marked there as that. And ADP stands for at position, so preposition or postposition, and adjective, noun, verb. So if we look at adjectives, we find that adjectives in more than 50% of the time modify the word that's right next to them. So you don't really need to look anywhere else in the sentence but just one position over. If you then take 2 or 3 or 4, actually if you stop at 3, cumulatively you have covered more than 90% of the cases. And so for adjectives, you really need to look in a very local window, which is not too surprising. But what is, was a little bit more surprising is that even for verbs, you have the subject, for example, just to the left of it. So 30% of the cases, you have a distance of 1. Another 20%, you have a distance of 2, and then 10% here. So even for verbs, more than 60% of the modifiers don't have a length more than 3. So what we can do is to say, okay, when we're trying to figure out which word is modifying another word, we don't need to look at the entire sentence. We can just look at very local window. And that's a way to save computation by saying, rather than trying all pairs, let's just try things that are local, and then only if we don't find something there are we going to look outside the window. And that was sort of the main intuition for making these parsers a lot faster and more accurate. And then once you can do the analysis more accurately, it supplements this question answering thing that I showed, and I'll show some examples of how we use them in translation to improve the translation quality. Unfortunately, the models struggle with sort of more semantic types of decisions. So I ate pasta with tomato sauce versus I ate pasta with a spoon. If you take all the possible parsers that are out there, I'm willing to bet that most of them will get 50% accuracy on these two sentences. They'll either say that in both cases this prepositional phrase with something is modifying the noun, or they'll say that in both cases it's modifying the verb. So the issue is that in order to decide what the right analysis is, so I can show the parse trees, basically in order to say this phrase with a spoon is modifying how you eat versus it's modifying what's on the pasta with tomato sauce, you need to know something about the verb, something about this object of it, the noun, and then also about this preposition and this other noun so that you know what combines with what. And so there's a lot of lexical items that are involved, and no matter how large your corpus is, to get kind of trilexical statistics of verb, noun, noun, potentially even with a preposition. So 4 words in all combinations, it's just going to require a huge amount of data, and requiring a linguist to label that for you is not going to scale, because you can eat a pasta with many types of utensils and with many types of sauces and cheeses and other things. And so to be able to do the analysis right here, we need to take semantics more into account. The problem is that typically we do syntax first before doing semantics, because syntax is supposed to help us get there. And so it's a bit of a chicken and egg problem, but this freebase
database that I mentioned before, it actually contains not just people and places, but it also contains a lot of English words. And it will tell us that pasta is of type food, and tomato sauce is also of type food, while spoon is of type food culinary tool. And so now if we can abstract away from the individual words and just say, okay, I'm eating something of type food with something of type tool, well, probably the tool is modifying the verb because I'm not going to eat a tool, while food and food should go together, and so this analysis seems to be wrong. The problem is that there's also lots of other entries for what pasta and tomato sauce and spoon could potentially be, and we need to kind of disambiguate what's the word sense in this particular case in order to use it. And that's something that we're trying to get at these days. Another problem is that we have sort of new words and changes in domain and usage of phrases. So if I give you the sentence, text Gonzalo that I'll be late for my talk. If you take a model that was trained on document text, this is the analysis that it produces. It says text is a noun, and it then gets the part of speech tags of the rest right, but because it doesn't have a verb, it produces this weird fragment type analysis where it says, okay, this is some type of noun phrase, text Gonzalo, and then there's some modifier to that. But it makes no sense because it got the word text wrong. And so we would like to be able to go in and say, no, 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 text in this particular type of utterance is actually a verb. And please analyze it as a verb. It's an imperative verb, and then everything else falls into place and becomes much more meaningful. But it's hard to sort of anticipate these changes in usage and to declaratively kind of write that rule down, because then we will go back to these rule-based approaches where you write a rule, but then you need to write a rule that is an exception to the original rule, and we kind of have shot ourselves in the foot. So that's, in my opinion, an open question of how we can do this in an elegant and principled way. One thing where we have an answer, so these were two kind of open questions of things that we're working on or that I think are interesting to work on. One thing that we have made some progress on is to say, okay, if we have just documents and we want to transfer the information, kind of the models to queries and to get better at analyzing queries, how can we do that? And so here's a query, by Brave 2012 soundtrack. If we use our part of speech tagger that we trained on documents, it will say that Brave is trying to decide between adjective or noun, and it's going to say it's an adjective. Why would it think that it's a noun? Like, it's a perfectly fine adjective, and it's used like that in document text all the time. On the other hand, if we look at the snippets here and the way that it's used, it's actually capitalized. But how many of you use capitalization when typing queries? Very much nobody, because you as a human don't need that cue. You understand that in this particular case, brave is not the adjective, but it's referring to the movie. And so what we can do is we can analyze these snippets and then transfer the tags back to the query and thereby create offline a set of queries that have been analyzed with part of speech tags, and then we can use that to train our part of speech tagger, and then we'll have not only learned that brave in queries can be both adjective or noun, but also we'll learn something about the word order that people typically use in the queries. It won't be perfect because there'll be lots of errors that we propagate, but on the other hand, we can get unlimited data for free that way, and so we can retrain the model, and we get this analysis now correct. And here's some numbers, sort of the baseline. This is an alternative approach that was proposed, and then we can compare using all snippets versus the top one and versus the one that the user clicked. And even though these differences are small, it's nice to see that the one where the user clicked seems to have the most information, and that makes intuitively sense, because if something is ambiguous, then we want to get help from the user. So yeah.
Do you keep track of which choice the user chooses?
Yeah, I mean, that's the click one, right?
But millions of users, that.
So yeah, what we do is we do this once in a while. We don't do this all the time. But basically, we get some data from the logs. We get a few million queries with the clicks. And then we just average over, kind of for the same query, we average over the different results. And then we add that data to the training data. And we retrain the system on this. And we do this once in a while. Other questions? Yeah.
Translate, when you go to Google Translate, is the system translating live, or is he going back to some logs or previously translated?
It's all
text?
live.
What?
It's live.
Okay.
Yeah, same thing with the queries. I think Google has released statistics. I don't remember on top of my head, but I think about a third of the queries every day are seen for the first time ever. So a third of the queries are Facebook. Not quite, but like there's a lot of kind of one-word queries that are navigational, where somebody's just trying to get to a web page. But then there's a very thick tail, and there's no way to pre-compute the answers for those. There's some caching going on for the frequent ones. And Google Translate for individual words it's just a lookup, so it doesn't need to do much. But then when you look at sentences, there's a very long tail of things, and so therefore it doesn't make sense to have kind of pre-compute, well, I should relativize it. We use our phrase table. Basically, our dictionary is not a word-to-word dictionary, but it contains phrases. And so I think they use phrases of either 5 or 7 words as the maximum. So if you have something that's less than that, it can potentially be just answered by looking it up. But even for that, they'll try, okay, we can look it up directly, or we can try to synthesize it out of smaller pieces, and they'll compute it on the fly and see which one scores better, and give you the better one. Yeah?
So I think nowadays we can download Google Translate dictionaries into our smartphones.
Yeah.
Some languages. And how does this work? Because when we go to google.com, you have many resources available to you, and it's running in our smartphones, probably much harder. So
Yeah.
that's the challenge there. How did you manage it?
So it's a smaller model, basically. It has been pruned to contain only the most frequent things. I mean, most. It's still a very good translation model, but it's kind of, as I said, like the phrases will be smaller. Like it won't have things up to 5. It will have things up to 4 or 3, and it will keep only the things that appeared a certain amount of time. So the rare things will get removed, and as a result, the translation quality will be a little lower, and the team spend a lot of time trying to find the right trade-off of, okay, how aggressive can we be in removing things? Because just using kind of absolute thresholds is not necessarily the right thing, so they use entropy-based metrics to figure out, okay, what is likely and unlikely, and where does having this 5-word sequence really add value, because it's different than having the 3 words and 2 words stitched together, because it's an idiomatic expression, for example. And so they kind of spend a bunch of time trying to optimize it so that it contains the information that's really needed, and the user doesn't see the performance impact too much. Other questions? Okay. Gonzalo, you said till 4:30? Yeah. Okay. Well, I think I want to let people go at some point too. So, okay. Then I will skip the universal part. So what I said kind of that we do on English, we try to do for other languages as well.
And in many cases, we can just pay linguists to annotate data for us, and then we can just take the English models and train them on Spanish and then or Portuguese, and then they just work. But getting linguists to label data is A, expensive, and B, takes a lot of time. So in order to get things to work for many languages, we also try to project information from one language to another by taking the data that we have for translate. So we have sentences that are translation of each other. We can analyze the English side, and we transfer the information to the other language and train a model then on that projection. And that would have been something that I could have spent 10 minutes on, but instead I'll go directly to translation examples and then some of the kind of new things that we do. Before going in there, I will start with a little anecdote. So the question sort of is, or I think it has been answered now, or most people will agree on the answer, but in the early 2000s and mid-2000s, it wasn't very clear whether syntax was going to be useful and whether these complex models are really necessary, or whether we can just learn everything that we need to learn from raw text from parallel sentences. And so on the left here, we have Kevin Knight and Daniel Marcoux, who are two leading researchers in machine translation, and Franz Auch here, who was a postdoc with them, but then came to Google to start Google Translate and led the team until last summer and made Google Translate basically what it is. And Franz didn't really think that syntax is important, and so he focused on just scaling things up. And as I showed with these graphs, more data just really, at the beginning, helped a lot, more than smarter models. On the other hand, at some point you have all the data that there is, and you need to kind of add a factor of 10 more data, and that's just going to take years before it's produced. And so you need to also have smarter models. And the question was like, okay, which one is going to prevail? And at an annual competition, they made a bet that said, okay, whoever loses to the other will have to wear a shirt saying, I lost the syntax bet. And the first year, Google blew out everybody. The second year, it was split on Arabic. The syntax system won on Chinese, the flat system, and then they stopped the bet. But it prompted Daniel Marcoux to say, basically, Daniel used to always say, syntax will improve. Franz said, syntax doesn't help. And that then kind of was related to a quote from Fred Jelinek, who passed away a few years ago, unfortunately, but who started speech recognition the way that we do it nowadays, 30 years ago, and who was on the forefront of the statistical revolution. And he once apparently said, every time I fire a linguist, my performance goes up. And that was referring to the fact that kind of rule-based systems just don't scale, and using data and statistics is a better way to go about things. And so in this case, adding syntax means actually adding more linguistic information, and that prompted Daniel Marcoux to say, every time I hire a linguist, my BLUE score, which is a metric for evaluating translation quality, every time I add a higher linguist, my BLUE score goes up. And so one of the ways that we have been using syntax or linguistic information in Translate is to do what we call pre-ordering. And we saw in the Japanese example at the beginning of the talk that the word order is so different that translation quality really suffers. And so to make the translation problem a little bit easier, what we do is we parse the sentence, and then we change the word order so that it matches what the target will be. So in this particular case, we took an English sentence and we reordered it to look like a Japanese sentence. So you could call it Jenglish or something. Where in Japanese, in English, your word order is subject, verb, object predominantly. You can move things a little bit, but that's most of the time the case. In Japanese, on the other hand, the verb is pretty much always at the end. It's subject, object, verb. And so you need to listen to the Japanese speaker till the very end for him to say the verb. You cannot interrupt him because you're not going to know what he's going to say otherwise. That's why they're so polite. in Romance languages, you can interrupt somebody because you already know what they're doing. And so here we're taking the English sentence, changing the word order, and then translating so that we can still do some reordering, but we don't need to do as much reordering. And that really improves translation quality. And so even though France initially didn't believe in it, once people showed that this can be done, it was launched in Translate, and it has been part of Translate for 5 years or so, and we've added more and more languages. And one simple approach of how to do it is to just say, okay, we're gonna go through the sentence and take for each word the words that modify it, and try to predict the order in which they appear on the target side. And so if we number the words as 0 is the head, 1, 2, 3, then we can check all orderings. Well, how many orderings are there if there are n words? N factorial, yeah. So that's pretty bad news, you would think. And in algorithms class, you've learned anything that's n factorial you don't touch. Well, turns out language is actually not that bad because n is not going to be in the thousands. Typically, a word will have 2, 3, 4 modifiers, and n factorial is not that bad. And if it has more than 5, well, then we're not going to check all permutations. We're just going to check the most frequent 20 or 50, and that will cover the majority of cases anyways. And so this brute force approach actually works quite well already. We call this the one-step reordering thing, where we just learn a classifier to do that. But you can do actually better by splitting the process up into 2 steps, where you first say, okay, is the word going to go before or after the word that it modifies? And this is called pivot classifier. And that splits up, takes the pivot word, the head word, and then puts some stuff before and puts some stuff after. So if you had 4 words, you've taken out the head word, so you only have 3 that you could have at most on one side and 0 on the other. But more often than not, things split evenly. And at that point, you've reduced the problem from 4 factorial, in this case, to 2 factorial. So 2, this one is already in the right position, and this one is in the right position. So in 2 steps, you can do this. And this first classification step can be done with 96, 97% accuracy, so it's very accurate. And then when we look at translation quality, we get these huge gains compared to not doing any reordering, and then compared to doing a rule-based one, where people wrote rules, or we learned the rules, and then this one-step approach beats that typically, the green bar. And then the blue bar, the 2-step approach, is always better. And this is now used when you go to Google Translate in many cases. So, do you have a question? So this is this blue score, and it basically, it looks at sequences of words, so-called n-grams, and counts, like we have the translation that was produced by a human. Typically, we'll have multiple translations. We'll have 3 or 4 translations. And then we take the system translation and we check how many 4 grams, sequences of 4 words, did we get in our machine translated output that matched the human translation. How many sequences of 3, 2, and 1, and then we combine them in a weighted average. It's not perfect, but it's an automated measure that you can use during development. And then before actually launching something, we will do a human comparison, where we give a human 2 translations, and we switch always left and right so that he cannot find a pattern. And we ask them to say which one is better. And then we check sort of, is the new system better than the old one? And if it's consistently better, then we launch it.
Hello. So I just wanted to ask, the improvements that you are getting, is it just because like the phrase-based system is really bad at doing reordering, like long-distance reorderings, because it is using a very, I'm not sure what model you are using, but
Yeah.
if it's something similar to the MSD model, it just makes some local assumptions about the reordering process.
Yeah, so I mean, that's why, like, here, Japanese and Korean, you see 7 blue points. This is huge. But this one, for example, where the gains are smaller but still big, this is a syntactic system, so it's a tree-to-string system. For Romance languages, the gains are much smaller. In the paper, You can look like we did Europower languages, and we got some improvements on the WMT things as well. But here, if you look at these languages, there's typically a systematic change in the word ordering, and you need syntax to fix that. But even with a tree-to-string system, we're seeing some improvements. Yeah.
I was wondering, what you do when, for example, a user wants to translate something from a language to another, but they do mistakes in writing words.
Well, we hope that they made the same. Somebody made the same mistake on the document side where we extracted the parallel text from.
Or for example, when you have a word that's not, it's like a name, but it's very close to an existing word.
Yeah, so there's, right now there's no explicit control for that. There's no explicit spell checking and fixing. And we do try to do specific things for entities sometimes, so that we detect them and translate them differently or kind of transliterate them if we don't know them. But for misspellings, it's just don't misspell, please. It's going to break down. And I think that there have been experiments where, because on google.com you get the did you mean thing, and there's a very good spell checker there. I think there have been experiments to try to use it, but I'm not sure kind of what happened there and whether they're used or not. But overall, it's just spell checking is quite hard. And if you take something that somebody spelled in a particular way and you correct it to something that they didn't mean, it's very annoying. And so for many of the kind of frequent typos, we will have them in the phrase table because somebody had that typo on their blog as well and they translated it, and we get some of those. But if it's really not there, then the word will just get preserved and will stay the same mistyped word in the translation. And that's easy to spot and then correct manually. Other questions? Okay, so I wanted to then just show a couple of examples of things that I think are cool and hard, and things that I personally want to work on in the next year. So hopefully they'll start working at some point. So here is a query. Who was the president when the moon landing happened? Well, if I asked you this question, you would probably say, okay, when did the moon landing happen? You can answer that with Google. And then you could go back and say, well, who was the president in 1960-something? And you'll get the answer. I think the computer should just do that for you. And especially when you ask that on a mobile phone, you don't want to ask many questions. You want to just do it in one go. And so I think that's an interesting query to try to kind of think about how can we do it. But we don't want to write a rule that says, okay, when the moon landing happened, get the date. And like, it needs to be general, and it needs to be able to take these when phrases and figure out what to do with them, because they're not always kind of easily mappable to a date, but oftentimes they are. Another query is biggest Portuguese city without a first division soccer club. Since I'm a soccer fan, well, Wikipedia will give you Primeira Liga, like it will have a list of the teams. Getting a list of the cities and their populations shouldn't be hard either. And then you just need to intersect them, sort them, and you're done. If you are on a computer, you can open 2 tabs and visually inspect it, or you can put them in a spreadsheet and do it pretty quickly. I think the computer should be doing that for you. And I think it's not trivial, but it's within the reach of what we can do nowadays. Something that's kind of a little bit harder potentially, and just kind of exemplifies the variety of things that people can ask, is a seafood restaurant near me that starts with R. Like, I remember last time I was here, I went to this place, it was something with R. Like, what is it? And if you type that into Google, like, you don't get anything. On the other hand, if you just type something simpler, seafood restaurants near me, it's like, oh, amigo, yes, that was the one I was looking for. Like, and so anticipating all these needs is going to be impossible. We cannot encode that by hand.
We need to learn from the interactions and from the query stream and from the things that people type. And so that's kind of the idea, is to try to use information that we already have, like these lists of restaurants, use the queries, use the document side analysis that we can, and combine it. And supplement it with linguistically kind of motivated data or things that we ask linguists to label. And so kind of schematically, you could think about it like we have some small amount of labeled data. It's very expensive, and it's small. But then we have these container loads of unlabeled data. And we don't really know exactly what's in there, but because it's so much, like the correlations in there can help us learn. And so in addition to that, we have a lot of structured data in Wikipedia or other databases. And we can use that to then kind of put it in a nice model and learn something that will hopefully help us get towards sort of language understanding. So I'll stop here. Thank you. Any more questions? Yeah.
So among all the things that you showed us today and in general at Google when understanding language, which are the ones that are consuming the most resources in terms of machine, CPUs, whatever?
And I guess I forgot to say that at the beginning, like I work at Google, but this is my personal opinion, and it's not endorsed by Larry Page in any means. I did not ask him for permission. So in terms of computational resources, it just like varies. Like there's analyzing the web, like there's machines that do that all the time, kind of crawling. There's many machines dedicated just to analyzing queries. But for example, translation is a huge system these days. I think last year they released the number saying that it's a billion sentences every day that get translated. And it's a computationally non-trivial task to translate them. On the other hand, the volume of speech queries is rising as well. And so if you have a speech query, you need to do first speech recognition and then do all the other work that you're doing on top for just regular queries. So like there's a lot of computation kind of and things going on live as you search things. There's a lot of systems that require huge amounts of training data and kind of offline training. Typically, the language ones are actually, I would say, somewhat well-behaved, because if you think about video, there's just so much more information. Like you can express text in a few bytes, but people are uploading videos and they want to make them searchable, and the amount of data that YouTube is processing dwarfs some of the kind of the language kind of understanding applications that I showed. But yeah, like there's a lot of stuff happening every time like you search for something. I think somebody at some point Google released something that's saying like every Google search you can power 80-watt bulb for an hour or something. So on the other hand, our data centers are in they use clean energy, and Google has a carbon neutral footprint, so it's doing a lot of renewable energy. So please continue searching. It's not that you're burning down the planet, but it does involve a lot of computation every single search, and kind of also storing all the Gmail and YouTube data. It's a lot of stuff. So I didn't quite answer your question, but I can't kind of talk about explicit machine numbers, and I actually don't know the recent numbers anyways.
You mentioned that you have Google has machines learning the web, going through web pages. Do they also do that for videos, or does it take too much resources?
So there are, I mean, kind of if you look at image search, there's a lot of stuff processing images, and there are experiments for analyzing videos and not just retrieving what's in the caption or kind of in the description, but actually looking inside the video and automatically recognizing, oh, there's
somebody singing or somebody playing the piano, and when somebody searches for that, to surface that. I don't know personally how much of that is launched right now. I think some of it is, but I don't know exactly. Like one thing that is launched for sure though, in terms of video analysis, is compare kind of copyright infringement detection. So finding out that this clip, like these 30 seconds, are coming from another video that you don't own the copyright to, and that the copyright owner has said nobody's allowed to upload that. So if you kind of try to upload segments from movies or from sports events, that will get detected, and that is run on every video as it's uploaded. So we do analyze the videos for sure. Behind you.
So you talked about how you use syntax in translation, but then there are a lot of languages that have lots of like morphological variants in terms of words. And so, do you do anything in that field? Like, if you have a Arabic word with a different suffix,
Yep.
can you translate it?
We do some. So we do some on the source and some on the target. We use morphological analyzers on the source side to improve syntax, and then potentially do some stemming and things like that to then translate. And then we also try to get agreement right on the target side. So in an extreme case, you could imagine a model. I'm not saying we're doing exactly that, but like one could analyze the morphology on the source side, strip it down to the stem, and then have the morphological features, translate the stem, and then have the morphological features, and then generate the suffixes. We're not doing that, but it's going in that direction, that we want to do more explicit modeling of morphology. Yeah, it's mostly supervised. At least the things that I'm aware of. The other things you get a lot sort of, yeah, implicitly from your language model. But agreement errors on the target side are really annoying. Humans get upset when you have an adjective and a noun right next to it and you get them wrong. Typically you don't make that mistake because the language model will fix it, but sometimes it does happen, or a noun-verb agreement. And it always in subjective evaluation, those things show up very strongly, and so we're trying to get better at it. But I think part of the problem is that everybody speaks English, and when you translate into English, you look at the output and it looks great. And you need to look at Russian output to realize how big of an issue it is. And so we have people who are looking at it and trying to make it better, but it's hard also. Oh.
I'd like to thank Slav for being here and coming to Portugal to give us this lecture. And there's a mini coffee break right there where you can talk to Slav personally. So,
Thank you.